Okay, April. Last time we talked about where's my okay talk about the transformation between domain and codomain. Well, your vector x is given, but we would like to represent that x with respect to a canonical base I. And for that transformation, we used a matrix to represent a linear transformation between domain and codomain. Mm, okay, matching notation will be I have t transformation of the vector, then that is represented with respect to identity matrix canonical basis. So the linear, and again, this is going to be, again, if we know, because this is now a vector, which is n tuple, right? N tuple, then can be written by matrix vector multiplication, which is x bar and I, right? That's the case of canonical basis. Now we interested in a new transformation of new um, vector representation of different bases. So we used that basis as B last time, and then we know that same B basis applied to the output. Definitely, that's Tx bar. Mm, Last time we okay, now the relationship between these two transformation of canonical basis and the new basis B was by this arrow, right? So let's have the same arrow. These two value on the left hand side and right hand side of this arrow must be the same because A or I mean D in general T is a linear transformation. So well, if you recall, my x vector was written as I times in the coordinate over here, which is this one, right? X. This is kind of recap that we had last time, but I won't take much time over here, so don't get bored. Please give me a 5 minutes so that I can actually develop my idea here. Okay, so there's matrix times vector multiplication. So this vector is actually represented by this matrix vector multiplication. That one is again represented by C matrix and the coordinate of the vector x with respect to B. Here C and B's are kind of same thing. C is here. Oh, by the way, my okay, wait a minute. I'm going to change the color here. This one. My this I and this I notation is kind of contradict the usage of these two. On the right hand side, I use this C to denote matrix, which is a collection of columns, whereas this B is the basis or the set of vectors, right? And then C is just like intentionally introduced to actually introduce change of matrix notation C. Therefore, I could have written this as a B if I follow the same as I did here over here. This kind of the notational abuse, but you got to understand that's how they develop. Well, at any rate, C is the matrix consists of basis vector of this B. Let me change this color in the white again. So the relationship between these two, again, if we from this, we can say that what is this one written? So I'm gonna separate this one. So if I write the equation for this one, then I'm going to pre-multiply C on both sides. So C inverse on both sides, right? And then I get I, and I get X bar, and then I, and it's going to be same as just yeah, that's it. So I, again, this becomes itself because identity matrix property. Look at this. That's the relationship. That's how the C comes from. That's how this guy and this guy related. In other words, this XB is written after you multiply C inverse to this guy over here. So I have to write C inverse over here. Therefore, this is C. Likewise, due to the linear property, and I'm going to have this one as C inverse, and this is C. That's how we got the relationship between D and A last time. So D is I have to move this here and here and here to get equivalent this direction, right? Therefore, I have to multiply X per P, this one over here. Then I apply C here to come over here, right? So C and A, and to come down, I get C inverse multiply. So so this is D times X bar B, right? Because I'm writing this part here. So therefore D was C inverse AC. T was C inverse AC. Okay, that was the first part. I mean the one that I showed you last time, right? Now how that? Okay, now, well, again, to answer the question in your email, and I guess yeah, I think you asked that question. I understand. How this diagonalization T? Remember in your writing you said P A P inverse, but it is quite normal to say the P inverse A P. Well, again, yeah, but you can argue that you can just make this P as a P inverse, and then we're going to get the same thing. But again, the second one is the common way of saying that diagonalization. So if you have any square matrix A, which is n by n transformation matrix, then P is the actually P is matrix of eigenvectors. P inverse is the inverse of P. And then how this is related to this thing? It's quite a similar looking, right? Yeah, there are definitely a good relationship between these two. So I get D, and I get, by the way, this D I'm sorry, this D is the new transformation of this D, whereas my different color, red, this D is where the diagonal matrix is, diagonal